Let's have a look at some surface area problems. So this first one here is a composite shape. It's a very common one that you'll see, which is a cone on the bottom and on the top a hemisphere. So this is two different bits. So for the surface area, there's going to be two pieces we need to add together. We're going to have the cone bit plus the hemisphere bit. So for the cone, if we're just interested in the cone, not the full cone, well, that's just pi rs. And for a hemisphere, which is an open hemisphere, right, we don't want the bottom, then we're just going to have 2 pi r squared, or half of 4 pi r squared, whichever you prefer. With this, we can substitute in our numbers, so pi times the radius, which is 8, times the slant, which is 20 for the cone, plus, didn't put the square, 2 times pi times 8 squared, because that's the radius. And with that, that'll give us our answer, which gives us 904.778, rounds up to 78, 904.78, and units is going to be centimeters squared. Okay, so that's one example. Let's have a look at this slightly more interesting shape here. Now this shape here has basically a rectangular prism with a cone on top. But this causes us some issues, and it causes some issues on the top face. For the bottom bit, it's pretty straightforward. We're going to have one front, one right, then the back's going to be the same as the front, the left is going to be the same as the front, but the top and the bottom are actually different. The top is this full thing minus this circle here. This circle actually is being subtracted off that. Because if you actually think about what shape of the top is, it's actually making this shape, where there's basically a hole cut out of it, which is that circle. But on the bottom face, if we think about what the bottom face would look like, well, on the bottom, you'd get just a regular rectangle. And then on top of that, we've also got the cone bit. So those are the pieces that we're basically going to be working with. So we're going to have, for surface area, we're going to have 2 rectangles, that can be the front slash back, plus 2 rectangles, which is going to be the left slash right. Then you're going to have 1 rectangle, which is going to be the bottom. But then you're going to get the weird bits. You're going to get 1 rectangle with a hole cut out of it, which is going to be the top. And then you're also going to get the cone bit. So, before we go on, let's deal with this top little bit here. So first of all, let's think about what the radius is going to be of this. So since it spans the whole width of the box, that means that's going to be the same as the 16 meters, because that's as far across as it actually goes. Because it does actually touch the far side, as you can see on the picture. It just doesn't look quite as big due to a bit of warping in terms of the perspective. So therefore the radius here is going to be, well, half of 16, which is 8 meters. Also, while we're doing this, we should also work out the height of just the cone. See, the box is 10 meters and the whole thing is 25 meters, so the difference of 10 and 25 minus 10, well, that leaves us with 15 meter tall cone. Alrighty, so now we're nearly ready to go. So let's jump into the formula section. We get 2 times length times width, that's for the front and the back. 2 times length times width, plus length times width. Now the next one's the interesting one. What do I do with this thing here? What am I going to write for this formula here, for this bizarre looking shape? Well, for this bizarre looking shape, it's going to be length times width for the whole rectangle minus pi r squared for the circle itself. So that's going to be the formula there. And then for just the cone bit of a cone, that's pi rs from our cone surface area. Alrighty, so for the front and back, so the front and the back is going to be 30 by 10 plus the left and right is going to be 16 by 10. The bottom is going to be 30 by 16. Now the top is also going to be 30 by 16, but we're then going to subtract off the circle, and the circle radius is 8, so pi times 8 squared. Adding to that, the cone, which is pi times the radius, which is 8, times the height, which was 15, as you can see there, that's the height of the cone. And with that, we now have everything we need to do. Now, this is a particularly large question, and so this is a sort of calculation you definitely want to check before you push the equals button, because it's very likely that a little mistake happens and it's going to ruin all of your hard work. So let's do that now. So the total surface area of this shape is going to be 2055.929, which would round up to 93. In this case, square meters. Alrighty, one last problem. Let's imagine that I've got enough paint to cover a sphere sized 2,500 square meters. So I've got enough paint to count the outside. Question is, what is the radius of such a thing? Well, a little bit of algebra is going to go a long way. So for a normal sphere, the surface area is equal to 4 pi r squared. Now I know the surface area we want, 2,500, is equal to 4 pi r squared. First bit of algebra, let's get rid of the 4 and the 4 on both sides. So divide both sides by 4. This with 625 on the left-hand side and pi r squared on the right-hand side. Now we need to get rid of the pi from both sides. So let's divide pi, divide pi. That gives us 198.943, which we're going to round down to 94. Is equal to r squared. The opposite of r squared is take the square root. And the square root of 198.94 is? The radius is equal to 14.104, which rounds down to 10 square meters. No, meters, because remember radius is measured in linear units, so just meters. So those are 3 sort of different types of problems and some strategies in order to actually try to solve them. The last one, algebra. The previous one, composite shapes and thinking about it visually. And for the first one, also to do with composite shapes. Alrighty, I'll see you in the next one. Goodbye.